second half of QED at one loop. And so Tibra did a lot of the hard work teaching you how to calculate things at one loop. And so for the remaining 2 lectures, we're going to extract all of the interesting physics contained in the vertex function. So our main object of study for the next 2 lectures will be the vertex function in QED at one loop. And as we'll see, there's lots of interesting phenomena contained in this diagram. And so today, we will compute the anomalous magnetic moment of the electron. So the magnetic moment of the electron is denoted as G. Its classical value is 2. And so the leading quantum correction to the magnetic moment of the electron is given by this diagram, and its value is denoted as G minus 2. So this is interesting for 2 reasons. So first of all, this is one of the first one-loop corrections that was properly understood in quantum field theory. Second, this quantity here is one of the most precisely known quantities, both in theory and experiment. Another reason this is interesting is that you can do calculate the same quantity for the muon, the anomalous magnetic moment of the muon. Muon is heavier, so loops of other standard model particles are also important. And for the muon, there's a 3.6 sigma discrepancy between the theory and experiment. This is could be one possibility is there's some new physics lurking there. So understanding this calculation is a simpler step to the first step in understanding the more complicated muon G minus 2 calculation. So that's what we'll do today. And then tomorrow, we will discuss higher divergences. So we've seen in Francois and Tibra's lectures how to deal with UV divergences at encounter terms. We have not talked in much detail at all about higher divergences. And so we'll have to deal with these in a different way. So one of the first things I told you in QFT1 was that our observable quantities are cross-sections. Or cross-sections are one of the most important observable quantities. We'll see tomorrow that actually I was oversimplifying things, and not all cross-sections are observable. But you'll have to come back tomorrow to see precisely what I mean there. OK, so that's where we're going. And so today, we're going to calculate G minus 2. So what quantity are we going to look for in this diagram? So we can take the non-relativistic limit of the Dirac equation. And that will give us a Hamiltonian. Consists of kinetic term, Coulomb potential, and then another term that couples the magnetic field to the spin and orbital angular momentum of the electron. So this is, you can derive this from taking a non-relativistic limit of the Dirac equation. And so what G is it's the coefficient that tells us how the spin of the electron couples to the magnetic field. So this is what we're interested in calculating. And so I won't go through the whole non-relativistic limit. That would take substantial chunk of the lecture. But let's just see if we can, from the Dirac equation, find a term that looks like a magnetic field coupling to spin. So if we start with the Dirac equation and multiply by ID slash plus m, we get d slash squared plus m squared on psi is 0. And if we expand out the d slash, we get d mu squared plus m squared plus 2 f mu nu sigma bu nu psi equals 0, where sigma mu nu is pi over 2 times the commutator of gamma nu with gamma nu. And so this term here, if we write this out in the Weyl representation, gives us a minus e b plus I e times sigma and b minus I e times sigma, lower right-hand corner. And so this contains the coupling of the magnetic field to the spin of the electron. So the spin of the electron is just sigma over 2. So what we're looking for in our amplitudes is the coefficient of the f mu nu sigma mu nu term. That's going to be related to g, the magnetic moment. Okay. So at tree level, the vertex that describes how an electron couples to a magnetic field is just this elementary vertex in QED. So here we have an incoming electron and outgoing electron, and let's say our photon is incoming. And so if we allow our photon to be off shell, because we want this to correspond to an unconstrained external magnetic field, this diagram should tell us how an electron couples to a magnetic field. So this should contain the classical result that the G is 2.
Off-shell photon?
We're interested in an off-shell photon because we want to know how the spin. We want to know how the spin of the electron couples to an external magnetic field, and so we're not interested in doing just a scattering experiment of one electron off of one photon. That's what it would be if we imposed that. If this was on shell, this would be some real photon. But what we're interested in is looking at how an electron couples to an external magnetic field. So that's not just a single photon. It's some, we can think of it as some source that has to do with the A mu. And so we all know what the amplitude for this diagram is. It's just minus IE u bar of Q2, gamma mu u of Q1, epsilon mu of P. And let's give this a name. Let's call this, if we pull out an I in the polarization of the photon, let's call this I m naught, or m naught mu. And so there's absolutely no f mu nu, sigma mu nu term anywhere to be seen here. So where is the information about the magnetic moment of the electron? We can find that by this useful identity known as the Gordon identity. So the Gordon identity derived in just a few lines. It's an identity for that relates I sigma mu nu, Q nu minus P nu, UP. So this is the term we want. We want sigma mu nu coupled with the momentum of the photon. So F mu nu is, the terms in F mu nu are like the derivatives of A mu. So if we look at the amplitude, we want terms that are proportional to the momentum of the photon. So that looks like what we have here. So this is kind of what we want. So just using the definition of I sigma, we can write this as U bar of Q I squared over 4m gamma mu gamma nu minus gamma nu gamma mu Q nu minus P nu. And this is just 1 over 4m U bar of Q. We have a minus gamma mu Q slash minus P slash, then a plus gamma plus Q slash minus P slash gamma mu. And so we notice here that in this term, we have a P slash acting on an on-shell electron wave function. So by the Dirac equation, we have that P slash acting on U is equal to M times U. So P slash minus M U of P is 0. So we can use that to replace P slash acting on U with M and Q slash acting on U bar with M. So that gives us a 1 over 4m U bar of Q minus gamma mu Q slash plus 2m gamma mu minus P slash gamma mu U of P. And then if we just use the commutation relations, we can change the order of these two terms and then use the same identity again. So that will give us 1 over 4m U bar of Q, 4m gamma mu minus 2 Q mu minus 2 P mu UP. So we see here the term we have. This is just a U gamma mu, U bar gamma mu U. And we can relate that to the term we want, which has a sigma and the momentum of the photon. So that lets us write m naught mu in a form that makes explicit which term we care about if we want to calculate the magnetic moment of the electron. So we have two terms. And so this first term doesn't involve any gamma matrices. So a similar term would be present if we were looking at, say, scalar QED, where there's no possibility of a spin magnetic field coupling. So this term is not interesting for us. This term, on the other hand, has precisely the same form we want. It's the momentum of the photon times sigma mu nu. So it's a coupling of the magnetic field with the spin. So we want this term. So the coefficient of this term determines G. Okay. All right, so that's where the information about the magnetic moment is at tree level. And so what we're really interested in is the one-loop correction. So before we go about calculating that, let's just think for a moment about what form we expect our answer to take. So what we want to compute is some correction to this diagram. And when here we've got, so this in general would be the sum of all 1pi diagrams that have these external legs. And in general, just based on Lorentz invariance, we expect that our answer takes the following form. So we've got two external fermions. So it'll have a U bar of Q2 and a U of Q1 at the end. Then there's only 4 different ways we can make a Lorentz vector from P, Q, Q1, Q2, and gamma. So we can have some scalar function multiplying each of our vectors. And here, so these are scalars. That could, in general, depend on the momentum. Now, we know by momentum conservation that P plus Q1 equals Q2. So we can use that to eliminate one of the, so P, Q1 and Q2 are not independent. So we can use momentum conservation to eliminate one of these coefficients. So let's choose to set this to 0 by momentum conservation. So that means we only have at most 3 functions. But we can do better than that. So as you saw in tutorial yesterday, the Ward identity that you all saw in QFT1 holds off-shell as well as on-shell. So the Ward identity in this case is that 0 is P mu mu. If we replace the polarization of the external photon with its momentum, we get 0 by gauge invariance. And so that tells us that if we just plug in our form, the form of mu that we have, then we get F1 U bar slash U plus P dot Q1 F3 U bar U plus P dot Q2 F4 U bar U. And this term we can simplify using the Dirac equation. So U bar P slash U is, by momentum conservation, U bar Q2 slash minus Q1 slash U, which is our Dirac equation, U bar M minus M U, which is 0. So this term is 0. And that tells us then that these two terms are equal and opposite. We can simplify these terms using, again, momentum conservation. P dot Q1 is Q2 dot Q1 minus Q1 squared, which is M squared. And that's precisely the opposite of what we get if we multiply P dot Q2. So if we use this, then we see that the coefficients of these two terms are opposite. So F3 is F4. So in fact, there are only two free functions that we need to find. So the most general form of matrix element is minus IE U bar of Q2 F1 of P squared or M squared gamma mu plus I sigma mu nu over 2M P nu F2 of P squared over M squared. So what have I done here? So here I have just relabeled the small f's with big F's, and also noted that, so before I just said fi's were scalar functions. Bidimensional, so it's convenient to have their arguments be dimensionless, so they have to be a ratio of two things, two Lorentz invariant scalars. The fi's themselves should be dimensionless, bidimensional analysis. And the only Lorentz scalars we have available are P squared, M squared, the Q's squared to M squared because they're on shell. We also have Q1 dot Q2, which is related to P squared and M squared, since P squared is 2M squared minus 2Q1 dot Q2, and Q1 slash and Q2 slash are also related to M squared, to M by the Dirac equation, because they're sandwiched by on-shell spinors. So these have to be a function only of P squared over M squared.
P mu not set to be 0, but you set F2.
F2 to 0.
But how can you argue from the momentum conservation? Like it is also momentum.
So momentum conservation tells us that P1 plus Q1 is Q2. And so if we have three arbitrary coefficients of them, so whatever the coefficient of P2 is, of P is, so F2, we can just replace P with Q2 minus Q1. And so then we can just absorb F2 into F3 and F4. And so this term is the one that tells us about the magnetic moment. And we know at tree level that F1 is 1 and F2 is 0. So it turns out the relationship between F2 and G is G turns out to be 2 plus 2 F2 of 0. So the magnetic moment is measured at long distances, so at low energies.
F1, is that the coefficient of M0 mu? So is that M0 mu, right? The one there's a 0 in the left-hand side of M. If you go
in this board?
Yeah, left-hand side of M. Is that the same thing as?
This is
Now, in the first term.
the first term. Yes.
If I compare this to the thing at the top of the second board in the middle, what is F1?
So F1 is big F1 is the same as small F1, except that pulled out a factor of minus IE.
Yeah. Okay.
So this is the form we expect to find when we compute our one-loop diagram. So let's do that now. So this is the diagram we're interested in computing. So we've got incoming momentum is Q1. Outgoing momentum is Q2. We have a momentum here, K. It's one undetermined loop momentum, so this one will be P plus K. And we can call this one K minus Q1. And so what's the expression for this? So we can just follow the fermion lines backwards. Well, first of all, we have 3 vertices. So this is minus IE cubed, 1 loop momentum, integral d4k over 2 pi to the 4th. If we follow the fermion line backwards, we get a U bar of Q2. Then we run into this vertex, which gives us a gamma, let's call this one nu, this one alpha, and this one mu. So we get a gamma nu. Then we have the fermion propagator, I p slash plus k slash plus m, p plus k squared minus m squared psi epsilon. Then we have the vertex mu, so we get a gamma mu. Then we have the fermion propagator with momentum k, I k slash plus m over k squared minus m squared I epsilon. Then we have the vertex alpha. And finally, the U of Q1. And we've left off the internal photon propagator, which in the Feynman gauge, it's just minus I G nu alpha over K minus Q1 squared. So that's it. We have all of the tools we need to calculate this. So the first step is we can organize this a little bit better. This is minus e cubed u bar of Q2. So our numerator is gamma nu p slash plus k slash plus m, gamma mu k slash plus m, gamma nu. We use the metric. Then u of q1 here. And we have a denominator that's a product of 3 factors. So this is a, this denominator is b, and this denominator is c. Okay. So the way we can evaluate this is using the same trick that Tibra used yesterday. Introduce Feynman parameters to combine this denominator into a single denominator. And so we need a generalization of what he used yesterday, which looks just like you'd expect it to, except for it's a factor of 2, you have to remember. So we can introduce 3 Feynman parameters that add up to 1. And we can write it like this. So in order to use, in order to perform the k integral, we want to eliminate any linear terms in the denominator here. So then we can go to polar coordinates and evaluate the integral. So we want to write out xa plus yb plus zc, which is quadratic in k. But there's also linear terms from the cross terms in a and c. And so what we find if we expand this out, x plus y plus z times k squared, get a minus x plus y m squared from the fact that q1 and q1 squares to m squared. Sorry, from the m and a and b. And then we get the linear terms that we want to get rid of. And we're left with some other terms here, yp squared, z q1 squared, and the I epsilon. So if we complete the square, what we get is k mu. We need to get rid of these terms. So y p mu minus z q1 mu squared minus something I've called delta, which if you work it out, it's just minus xy p squared plus 1 minus z squared m squared. Okay. So now that we've written the denominator as in this form, we can perform a shift so that we can go to polar coordinates. So if we shift k mu to k mu minus y p mu plus z q1 mu, this shift eliminates these terms. It doesn't change the measure. The measure is invariant under this shift. So then we can use the techniques we learned about yesterday, dimensional regularization, basically, although we'll see some of the terms are actually finite, to compute the k integral. We'll come back to that in a minute. But before I do that, I just want to comment on the numerator. Okay, so the numerator this is the numerator. We can simplify using the commutation relations and the identities we learned about in QFT1. So if you do that, it takes the following form. So U bar of Q2, K slash gamma mu, P slash plus K slash gamma mu, K slash plus M squared, gamma mu minus 2M, 2K mu plus P mu, U of Q1. So all I've done is taken the numerator and used identities like the ones you're familiar with from QFT1, so things like gamma mu, nu, gamma mu. Gamma nu is minus 2, gamma mu, and similar identities for more gamma matrices. We'll go through that algebra on the board. Okay, so there's a bunch of terms here. Fortunately, some of them are 0, and others simplify. So we're interested in evaluating integrals of this form. So as we saw yesterday, by symmetry, this integral vanishes. So if we take k to minus k, we get a minus sign. So this integral has to be 0 because the denominator and the measure are even. So that gets rid of this term and this term. So we don't need to worry about those. We also have this term, which takes the form, looks like integral d4k over 2 pi to the 4th, k mu, k nu, over k squared minus delta cubed. So this has to be independent. So we're integrating over k, so it has to be independent of k. And the only tensor we have around that it could possibly be proportional to is the metric. So this has to be proportional to the metric. So that tells us that we can write this as an equality if we put in some constant. And so this constant c has to be equal to a quarter, because if we contract, multiply both sides by the metric to contract this, we see that g mu nu, k nu is k squared, which is c g mu nu, g mu nu. So c has to be a quarter. And that means that inside the integral, we can replace k mu, k nu with 1/4 g mu nu. 1 over 4. Thanks. So, and this is a generally useful technique. I mean, often we'll see this replacement in you're doing loop integrals. You can replace k mu, k nu with 1/4 g mu nu. Sorry, I'm missing a k squared over here. This has to a k squared for the units to work out. So it's not an equality. These two things are not equal in general, but they're equal as long as we're doing an integral over Okay, so those are the can use these identities to simplify this. And after some more algebra, which I will skip, we see that minus 1/2 and mu takes the following form. So we get a minus 1/2 k squared, 1 minus x, 1 minus y, p squared plus 1 plus 4 minus 4. So we get this term, this combination of terms times u bar q2 gamma mu of q1. So this has the correct form to contribute to F1. And so it's not relevant for the magnetic moment of the electron. And so we'll come back to this one tomorrow. It will be relevant when we talk about higher divergences. We get a second term. That is simpler. And this has the correct form to contribute to F2. So this one will tell us about the magnetic moment. But we'll also get a third term. And this one shouldn't be here. This should be 0. This is exactly the term we got rid of when we use the word identity. So if it's not 0, we're in trouble. We made some mistake. Gauge invariance is broken. So this has to be 0. But this is, in fact, equal to 0 once we do the integrals over the Feynman parameters. So to see that, note that this is the problem term is odd under x, switching x and y. But what we're doing is we're integrating this. We have an integral dx, dy, dz, delta x plus y plus z minus 1 of n mu over k squared minus delta cubed. So this is the kind of integral we're doing. And this part here, the measure, is even under x to y. And delta, which I wrote on the top board, is also symmetric. This is even under x, switching x and y. So the problem term has to vanish by symmetry. So this and we're OK. Means we didn't make a mistake. We didn't accidentally break gauge invariance by something we did. OK. So what we're interested in then is that second term. And if we just look at coefficient we're interested in, which is f2 of p squared over m squared. We see that this is 2m over e of 4i e cubed m integral over Feynman parameters. Integral over our loop momentum. Z1 minus c over k squared minus delta I epsilon cubed. OK, so the next step is to perform the loop integral. And to do that, it's convenient to make a Wick rotation. So delta may have poles. Near the real axis. So k squared plus delta minus I epsilon and minus root k squared plus delta plus I epsilon. So we can rotate, do a Wick rotation in this way to avoid the poles. And that turns our integral d4k over 2 pi fourth, 1 over k squared minus delta cubed into minus I times the Euclidean integral. And then this is an integral that you learned how to calculate from Tibra and from their special functions tutorial. And we recall that our general result is that this in d dimensions is 1 over 2 pi to the d, 1/2 delta d over 2 minus 3, gamma 3 minus d over 2, gamma of d over 2, gamma of 3, 2 pi d over 2 over gamma of d over 2. And so this integral, in fact, is convergent. So we've got a, since we're interested in d equals 4, we've got a positive power of delta. Negative power of delta, but there's no all of our gamma functions have positive arguments. So there's no divergence here. And so in the limit d is 4, this thing becomes, this becomes 1 over 32 pi squared delta. Okay, so we're almost done. So we've done this integral. This just gives us a factor of 1 over delta. All that's left to do is the integral over the Feynman parameters. And so the integrals over the Feynman parameters are non-trivial if we keep the non-trivial but doable if we keep the momentum. But fortunately, since we're interested in the magnetic moment, all we want to do is compute these integrals when p is 0. So if we take p to 0, so F2, so the p dependence in this integral is all hidden in delta. So delta was minus x y p squared plus 1 minus z squared m squared. And so this at p delta at p equals 0 is just simply 1 minus z squared m squared. So the x and y integrals become trivial in this case. So F2 of 0 just gives us a factor of alpha over pi, where alpha is e squared over 4 pi times the integral over the Feynman parameters. And this is an x. So the x integral is trivial to do. This changes the limits of integration for y. Y integral is also trivial to do. And finally, we can do the z integral and just get alpha over 2 pi, which, so this calculation was first done by Schwinger in 1948, and he had this result engraved on his tombstone. That's the most proud accomplishment. So if we compare this with our earlier formula that G was 2 plus 2 F2 of 0, we see that G minus 2 is alpha over pi. And of course, we neglected the order alpha squared corrections. So could compute these. But I thought instead of doing that, it would be better to talk about higher divergences. So yeah, these order alpha squared corrections there's 7 diagrams there. It took 7 years to calculate. So considerably more complicated than, I skipped a few steps, but small steps that I think you could all fill in a few minutes. This term is considerably more complicated to calculate. The order alpha cubed terms were also calculated. There are 72 diagrams. It took about 30 years to do those. And alpha to the 4th has also been calculated, not analytically, but by computers. There are 891 diagrams. And together, if up to alpha, including the alpha to the 4 calculations, the result, which is very famous, is so there are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 digits here. So this is one of the most, as far as I know, the most precise prediction in all of human history. In fact, it's so precise that there is, so this depends on alpha, the coupling of the electromagnetic field. And theory and experiment, both for G-2 are both so accurate, both to this more than 10 digits, that there's no better way to determine alpha to make a comparison. So these are, as recently, this is used to define the electromagnetic coupling. Other experiments that try to measure alpha only can go to 8 or 9 digits. So this is a very impressive achievement.
At which order is this?
This is alpha to the 4th. Some of the alpha to the 5th is a work in progress. So people are, at least one person still working on this that I know. So.
That person is also working on quantum computers, right?
Anyway, so this is one of the celebrated results in QED. And so as I mentioned earlier, you can do the same calculations for the muon. So all the same diagrams are there. The muon couples to the photon in precisely the same way. But because the muon is heavier, you need to include the interaction of the muon with other particles in the standard model. And so for the muon, both the theory and the experiment are not nearly as good. The QED part is under control, but the interactions with quarks and gluons and other standard model particles are less well understood, and it's a harder experiment to do. So, but there's currently a 3.6, was what I said, sigma, 3.6 sigma discrepancy. Yeah.
Would there be a point in which, if we were to calculate higher loops for QED, like just do it, would there be a way to actually detect the standard model corrections to this by doing it more precisely, or?
Standard model would correct this. They're much smaller in the case of the electron because the electron is many times lighter than the muon. At some point, though, even beyond the fact that we can't measure alpha in any other way, so we can't really test the last few digits of this prediction. We know that, so we're doing perturbation theory. So we switched the sum and the integral. So this is not a convergent series. This is an asymptotic series. It has 0 radius of convergence. So this is somewhat miraculous that it actually has this good of numerical agreement. So it's an asymptotic series. It's only guaranteed mathematically to be valid in the limit that coupling goes to 0. But dealing with finite coupling here. Okay, so that's G minus 2. So in the last few minutes, I just want to comment on the other terms, F1, and give a preview of what we'll talk about tomorrow. And so F1, so we know at tree level, F1 is just 1. So we don't have to keep looking around this 1. Let's extract out the interesting part of F1, which is just F2 minus 1, and let's call that little f. And so along the way, we actually did, we computed all of the terms that come from this diagram. And so in particular, we computed f of p squared over m squared. And collecting our results from before, what we get is this expression. And plugging in our value of delta that we calculated before, delta was m squared 1 minus t squared minus xy p squared q. Okay, so this is not nearly as simple of an integral as the one we just computed. But we can understand, based on this expression, some of the limits. So the first limit we might be interested in is the UV limit. So in particular, we see from this expression that this integral is UV divergent. So for large k, we can neglect all these terms. Can neglect all of these terms. This goes as integral d4k, k squared over k to the 6th, which is logarithmically divergent. And that should be absolutely no surprise to you. Tabor told you that this diagram has a UV divergence. He calculated using dimensional regularization what counter term we need to cancel this off. So this is absolutely no surprise. So we need a counter term here to renormalize this theory. This integral has a new and perhaps surprising feature. If we look at the IR, So particulars, so if we want to look at the IR, let's take the photon momentum to be 0. And let's also take K to be small. And so in that limit, these terms go away. This term goes away. This term goes away. And we're left with this integral here. The m squares will also cancel. One of them will. So in that case, f of 0 looks like 1 over z squared cubed in the denominator. So this seems potentially dangerous when z approaches 1. So let's look at this integral also for z approximately 1. And so in that case, f becomes minus probably miss a factor, but something like e squared over m to the 4th integral dx dy dz delta x plus y plus z minus 1. In the numerator, if we take z to be near 1, there's no problem. So this is just some constant. So we'll get a minus 4. This goes to minus 4. And so in the denominator, we've got 1 over z, 1 minus 1 minus z squared cubed. 3. And so we can evaluate the x and y integrals. And those will give us, we'll be left with an integral dz. X and y integrals will just give us a factor of minus 1, z minus 1. And this integral near z equals 1 diverges. Right, so we only get one factor of z minus 1 from the x and y integrals. It's the same reason we got a factor of 1 minus z when we did the x and y integrals up there. This is independent of x minus 1. So this diverges. And so this is something completely different from the u-v divergences we looked at before. We can't cure this using a counter term. And this problem is going to lead us to have to rethink what we mean by which cross-sections are observable. So we'll see tomorrow that the resolution of this means that we can't, not all cross-sections will be observable. And so this is new. We can't solve this with counter terms.
But when we put k squared to 0, couldn't we just put k squared to m squared, what we would expect, because it's the loop momentum of some kind of IR electron? Because then everything is fine, right? Because the crucial point was that we cancel the k squared down there, because that thing would make it finite. I mean, we set k squared to a constant.
Yes.
0.
So we're integrating over all k. So if there's any region in k where there's a divergence yeah. So I've been a little bit hand wavy here. If you come to tutorial tomorrow, we'll look at a systematic way to count or determine which loop integrals contain IR divergences and which don't, and try to understand what the cost of those are. But we'll examine it a little bit more in lecture tomorrow, but in tutorial we'll discuss that in detail. And yeah, so this is something new we can't solve with counter terms, and this means we'll have to rethink what our observables are. And we'll do that in case of electron to electron positron to muon anti-muon scattering. So we'll look at this tomorrow. We'll see. So in QFT1, you calculated this to one loop, sorry, at tree level. And tomorrow, we'll look at what happens at one loop, where these IR divergences will be extremely important. Any questions? Okay. That's all I wanted to say for today.